In this video, we're going to have an introduction to colligative properties and the colligative property osmosis. So first, let's define colligative properties. So if you look right here, here's the definition right there. And so it's a property of a solution that depends on the concentration of the solute. So it depends on concentration, but here's the kicker. It's independent of its identity. So for example, if you had sucrose, or with sugar, let's just say sugar, or if you had table salt, these colligative properties don't depend on if it's sugar or table salt, but instead the concentration of the particles in that sugar or in that table salt. So this is something that depends on how many particles are present, not what those particles are. And that's what a colligative property is. So it's a property that depends on the concentration of the particles, but is independent or does not depend on what those particles are. They can be molecules, they can be ions. These properties don't care. All they care about is the concentration of the particles. Now, osmosis is a colligative property. So we're just going to look in this video at osmosis in general. And then on the next video, we'll see how this applies to red blood cells. Okay, so here is the definition from your book of osmosis. So it's the passage of a solvent, and for our situation, that solvent is going to be water, across a semi-permeable membrane from a loose solution of low solute concentration to high solute concentration. So I want to just think about a few of these words. So we're usually talking about the movement of water. And a semi-permeable membrane, this is a membrane that allows some things to go through, smaller particles to go through, but won't allow larger particles. So semi-permeable means that some things can permeate or go through the membrane. And we're looking at the concentration of the solute, not the concentration of the water. So in biological systems, when they're describing osmosis, they often talk about the concentration of the water. But in chemistry, water is the solvent. We're going to be talking about the concentration of the particles in the water, the solute. And for our situation then, if we think about that, the water is going to move from low solute concentration to high solute concentration. If we were using words that we learned about concentration, we might think of that as going from a dilute side to a concentrated side of the solute. Okay, so low to high is how the water is going to move. And it's the motion, the motion is trying to make it so the pressure created across the membrane is equal on both sides. And so what it's trying to do is equal out the concentration. Another thing is we look in the practice problems and in some of your homework, it will talk about osmotic pressure. And what we can know is that the side with the higher concentration of solute is the side with the higher osmotic pressure. Okay, so and we'll mention that again in a practice. Now, one thing I want to mention before we do, let's do it on the next slide. And we'll talk about this image in just a minute. But what I want to say is the type of solute matters. Okay, I'm going to write that at the top. Oops, I can't spell type. There we go. And by what I mean, or what I mean by that is it ionic or is it molecular, which is another word for covalent? Because covalent compounds stay together as molecules. Okay. Now, here's what we have to remember from chapters 3 and 4 in our textbook is ionic compounds dissociate in water. So if they dissolve in water, they dissociate. Whoops, I wanted the word compounds. Let me just erase and I can. There we go. Now, what does dissociate mean? Dissociate means, if you recall, that it will fall apart or separate into ions. And then the other thing I want to recall, because we're going to need to look at a formula and recognize if it's ionic, remember, ionic compounds are made of metals and nonmetals. Okay, so let me give you a few examples of why this is going to matter. So if I have sodium chloride and I dissolve it in water, sodium chloride is made up of sodium ions and chloride ions. So when I dissolve it in water, it dissociates, and for colligative properties like osmosis, it creates two particles. Remember, the colligative properties don't care what the particles are. In fact, they care more about how many particles are present, the concentration of the particles. So if I had 0.1 molar sodium chloride, really the concentration of the particles would be multiplied by 2. Because there's 2 particles, that doubles the concentration. So the concentration of the particles is double that. And you'll see why we need to know this. Let me give you another example. So let's say it's calcium chloride. And calcium requires 2 chloride ions because calcium has a 2+, and it will have then 2 chloride ions. So that has 3 particles. Okay, because it dissociates, it falls apart. Now, if it dissociates, then just as an example, if they tell me that the concentration of the calcium chloride is 0.1, well, really the concentration of the particles would be multiplied by 3 because there's 3 particles. So the concentration of the particles is 0.3. So it's more. So in terms of colligative properties, calcium chloride would even have greater impact than sodium chloride because it would have more particle concentration. Another example that I just want to show you is something like, let's do magnesium nitrate. Now, I just want to remind ourselves this would have a magnesium ion and 2 nitrate ions. So the nitrate ions are polyatomic ions, and they do not dissociate anymore. So the metal will dissociate from the non-metals, but if you have a polyatomic ion, it won't break into nitrogens and oxygens. So I just wanted to remind you of that. Now, I have one more thing I want to include, and I've kind of run out of space, so I'll try to write it across the top, although it's not ideal, and that is that molecular compounds, do not dissociate. Okay, so that means they do not fall apart. And so they only form one particle, because whatever the molecule is, it's not going to separate anymore. So there's always just one. So if you have a molecular compound, the concentration of the chemical itself is the same as the concentration of particles because they do not dissociate. So it's ionic compounds that their particle concentration will be greater than the other concentration. Now, molecular, how will we know if something's molecular? This is made of all nonmetals. So in our situation, it's covalent, and we know covalent compounds are made of nonmetals. So this image now that I had here, let's take a look at it and see what is happening. So on this first picture, let me get something here. So if I'm looking at this, whoops, I want to get a different, I'm going to get something that's a little thicker. If I look at this side, notice it has water, and then this little line right here is a semi-permeable membrane, and this is at the beginning, and we have water over the whole thing, but on the right-hand side, it has glucose. Now, when you just have water, that would be like 0 particle concentration, so that means it would be very low. And so then what happens, if you remember, we go from the water will move from the low side into the high side. And in this example, the right-hand side definitely has more particles, right? You see all the little green balls on the right and none on the left. And so now if you look at this second illustration, what you've noticed is this side is higher now than this side. And that's because the water has moved through osmosis, through that semi-permeable membrane to the other side. Okay, and then this side, the one with the higher particle concentration, has higher osmotic pressure. And that the osmotic pressure would be what it would take to force the liquid back down to equal. All right, so that's when they talk about osmosis, the water is going to move from the side with low particle concentration to high particle concentration. And as a result, you see a change in the water level. The low side will go down and the high side will go up. It's trying to equal out the concentration of the particles. And so we see this change, and that's what osmosis is. So let's take some examples where we might have to apply and ask ourselves, oh, how many particles? And, what would have higher osmotic pressure? So let's look at a few examples and try to apply some of these ideas. Okay, so this one gives us, it says, which pair equals the higher osmotic pressure? And what I want you to remember is this is the side that's going to have the higher particle concentration because it's the side the water is going to move to. And I didn't mention this on the other slide. Let me go back real quick. So on the second picture, I drew arrows only going one direction. But the truth is, especially once it gets equal, there's some water can flow back and forth between the membrane. It can go in both directions, but it will flow more in the direction from the low to the high until it gets equal, and then it will go equal back and forth. So I just didn't want you to think the water can only go one direction. It actually can go both directions, but it's going to be pushed in the direction toward the high side. All right, so let's look at these. Now, these are pretty easy when, do you notice on letter A, it's both sugar. So when you have the same substance on both sides, we know that the side with the higher concentration has the higher osmotic pressure. So if it's both the same, all you have to do is look, I wanted a different kind of marker. All you have to do is look at those numbers and the higher concentration, and it doesn't matter if it's percent concentration or molarity, it doesn't matter. As long as they're both the same. You could not compare molarity and percent concentration. We won't have that, but you couldn't. The concentrations have to be the same. So I have sugar on both sides. One sugar is on letter A. One sugar is 1%, one sugar is 5%. And so the answer, which has the higher osmotic pressure, the 5% sugar would have the higher osmotic pressure because it has, of two sugar solutions, it has the higher concentration. So if I look at the next example, this also is sodium chloride and sodium chloride. Okay, so again, in that situation, if you have the same chemical on both sides of the membrane, all you have to do is look at their concentrations. So I have a 3 and a 4, and the higher concentration always has the higher osmotic pressure. That's the direction that the water would flow. And so since it's both sodium chloride, let me use black again. They're both sodium chloride, then the higher concentration would have the higher osmotic pressure. So in both letter A and letter B, because there's the same chemical on both sides or that we're comparing, we just have to look for the higher concentration, and that one would have the higher osmotic pressure. Now, if you look down at the next one, we have glucose, and then we're comparing it with sodium chloride. So when you have different ones, different chemicals, okay, so you see how that is different than A and B. Then we have to calculate the particle concentration. So now we're going to apply what I was talking about in the previous slide. So the first one is glucose. Glucose is a form of sugar. It is molecular. They don't give us the formula, but it has carbons, hydrogens, and nitrogens. And so it only forms one particle. And so to figure out the concentration of the particle, of the particles, we're just going to multiply the concentration by 1, and so we get the same thing. Like really, we wouldn't even have to multiply it by 1. I'm just doing it for emphasis. Then if we look at the other one, so the other one is 0, oops, I'm going to change colors of the pen just to 0.75 NaCl. Okay, so that's an awful C. It should be capital there. Let me fix it. Okay, NaCl is ionic. Well, remember, ionic compounds, metals and nonmetals, dissociate, so they fall apart. And so that would be Na plus and Cl minus. So that's 2 particles. And so then to get the actual concentration, I take 0.75 times 2 particles. So the concentration of the particles is 1.5. So really, the sodium chloride has a higher concentration of particles, so it has a higher osmotic pressure. And so our answer for the second one is going to be 0.75 m NaCl. For the third one, would be 0.75 molar NaCl. And again, the reason we had to think a little bit more in depth about this is we had 2 different compounds. We had different things. Our substances in A and B were the same that we were comparing. So we didn't have to think about what they would make because they would both make the same number of particles. But in letter C, since we had 2 different things, we had to think about their particles. Okay, so now we're going to try another example to see, how do we apply this? So this is a problem from your textbook. And if you read the question, it says, consider you have two aqueous solutions. That means they're dissolved in water, separated by a semi-permeable membrane. That's the little line between the two in the beaker, shown in representation A. Okay, so this is where we're starting. Then it says, which diagram, B through D, so you have to choose B, C, or D, represents the final appearance of the liquids and the solute. Now, what we need to remember is that the water is going to flow from the one side with the dilute or the low particle concentration to the concentrated or the high particle concentration. And so you need to think about the particles. We have two kinds of particles. We have red particles, blue particles. We don't have to think about them breaking apart or anything. They're already broken apart. So I want you to think about how many you have on each side and what way the water is going to flow. So if it were myself, I would take a few minutes, pause the video, try to come up with an answer, and then unpause the video, and I will answer it. All right, so this is how I would approach this one. So if I look here, I'm going to count the blue particles. 1, 2, 3, 4, 5, 6. I have 8 blue particles on the left side. And then I'm going to count, I have 1, 2, 3, 4, 5, 6 red particles. Okay, so I know that the liquid is going to flow from the lower side to the higher side. It doesn't care that it's red and blue particles. So the liquid is going to flow from the right side, from the right side to the left side. Now, the liquid really does flow back and forth, but the main direction of flow will be from the left because this is the low side with 6 to the right, which this is the high side. So then if it's flowing to the left-hand side, from the right, which is the low side, to the left, which is the high side. So if I said it backwards, I apologize. It's flowing from the right to the left. And so since it's flowing that direction, I expect the left-hand side to rise. So it definitely would not be B. The particles aren't going to change side because remember in our semi-permeable membrane, it's water which is going to be able to flow back and forth. Now C looks good because it did have the left-hand side went higher. The particles are still separated. And then D, it's not going to be D. They got the particles to equal out, 1, 2, 3, 4, 5, 6, 7, but it's not about the particles equaling out, right? It's about the water flowing from the side with lower to higher. So the answer is going to be letter C. The particles themselves are not going to move, but the water is going to move from the side with lower particle concentration. In this case, it's on the right side with the red particles to the left side where you have the blue particles. And in that situation, the water level will decrease on one side and raise on the other. So the answer to that would be letter C. So I have one more example in this series. And this is again one from your textbook. The answer, I guess I didn't, when I got the illustration, I did not bring out the question. But what I want us to do is predict, well, I know what it wants us to do, predict whether we would expect number 1, number 2, or number 3. Now, on number 2, we would expect B to rise if it had the higher concentration. On number 3, we would expect A to rise. What would we expect? How would we ever expect it to stay like number 1? And that would be if both sides have equal concentration. Okay, so this is what we're going to predict on this first one. This would be that when we calculated the concentrations, both sides of the particles, both sides are equal. Number 2 would be, remember it flows from low to high, so then this would be one where B was higher. And number 3, if it goes from low to high, this would be when A is higher. So let's look at our examples. So the first one, side A, okay, so first I look here, they're both glucose. So then I can just look at the concentration, and I have a 10 weight percent and 20. So it's going to flow from the lower to the higher. So it's going to flow to B. So this one would end up looking, so B rises. And so this is number 2 up here. That's what I'm talking about when I say number 2. It's illustration number 2. B is rising. Okay, then I look at the next one. Okay, we have glucose and we have NaCl. Okay, glucose we know only has one particle, so its concentration is going to be 0.3, but the sodium chloride is going to have 2 particles. So it would be 0.20 times 2, which is 0.40. All right, so then looking at that, the 0.40 is going to be higher. So even though just looking at the 0.2 and the 0.3, you think, oh, 0.3. But because colligative properties don't care about what the particles are, the concentration of glucose particles are actually lower than if you take into account the sodium ions and the chloride ions. So this one is going to flow from B to A. So A rises. And this one is going to be then, the second one is going to be letter B. I don't know where to write it. A rises is going to be number 3, is letter B. So picture 3. Now, pure water is always 0 particles. This is glucose. I don't care what water's with. It's going to flow from the, It's going to flow from the pure water to the glucose. So this is a side, so B is going to rise. Let me do that answer in the black marker. So B is rising. So that's picture 2 above. Okay, same here, just to emphasize. We have pure water again, and here's sodium chloride. I don't care what water is with. Water always will have the lower concentration, so it's going to flow from the pure water to the other side. And so we're going to have A rises. So that would be picture number 3 above. And then this last one, we have sucrose and sucrose. So when you have the same, you don't have to worry about the particle concentrations. It's going to flow from low to high, so 1% to 3%. So it's going to go this way. And so we're going to say A rises. Whoops, A. Oh, it looks like arises. Let me make, so did my other one, but I'm saying A rises, and so that's number 3. Now, they did not have any examples that were number 1. Let me give you an example. I got to think about it in my head. So let's say I had 0. No, I'm going to change my numbers here, okay? Okay, so I have 0.1 calcium chloride and 0.15 sodium chloride. And so when you look and I say, okay, these are not the same thing, so I have to figure out their particles. All right, so just a second. Looking here, so calcium chloride has 3 particles because it has 1 calcium and 2 chlorine. And remember, I know it has particles because it's an ionic compound. It's metals and nonmetals. So to figure out the particle concentration, I take its regular concentration and I multiply it by the number of particles. So the particle concentration is 0.3. Okay, that's particles. And then on the other side, is sodium chloride, and it has two particles. It has a sodium ion and a chloride ion. Again, it's metals and nonmetals. We know ionic compounds dissociate, so when you dissolve it in water, you're going to have ions. So then I have to take the concentration of the solution and multiply it by the number of particles, and I get 0.3. So then I have 0.30 molar particles. Okay, notice even though these two substances are different substances, when I calculate their particles, they have the same concentration. So neither side has a higher osmotic pressure, and the liquid will move, the water will move freely back and forth in both directions, not causing either side to rise. So it's not going to move more in one direction than another because their particle concentrations are equal. So that would be an example where you would get the picture number 1. Let's see. Okay, because the sides remain equal because both sides have the same concentration of particles. All right, so in the next video, we'll continue this idea of osmosis and of the water moving, but we're going to be looking at red blood cells.